take a look at question 3, which was more difficult in that it's more abstract, but you're still following the process that we're always following with shapes like this, where we've got one shape added to another shape that we know, or one shape taking away another shape that we know. We don't actually have numbers, we only have letters representing the important dimensions. First one is very straightforward. This is a semicircle, and we want to find the area of the shaded area. So the area of a circle is, of course, pi r squared, which means the area of a semicircle is going to be half of that, a half pi r squared. You can just write it like that, or you can write it as a single fraction, pi r squared divided by 2. A half pi r squared is probably the way that we're most likely to think of it. So be careful, when you write something like this, it can look like the pi r squared is under the line. It's just a half, is actually multiplied by the whole thing. So that was for part A. For part B, we're also going to use circles, and the shaded area here is going to be the big circle take away the small circle. So what you need is the formulas for both of those. My big circle is pi big R squared. My small circle is pi little r squared. That is fully acceptable as an answer. Pi big R squared minus pi little r squared. I would encourage you, however, to factorize whenever you see a common term like that. So you could write that like that, and then we have the difference of two squares. So we could write that as pi big R plus little r, big R take away little r. All of these are valid answers to this question. They're all formulas that mean exactly the same thing. Okay, part C. What kind of a shape do we have here? It doesn't look familiar to us at all, but as I want to say over and over, it's always regular shapes. Shapes that we have formulas for will always make up the problems that we have here. So they've noted that each of these is the same length, and we can see that something is cut out. And what's cut out is a quarter circle. A quarter circle is cut out from each shape here, each side here. And because the radius of my quarter circle is A, that's going to be the same on every side as well. So reconstructing the shape that was cut out, what we can see is that the shaded area here, let me move this up a little bit. The shaded area is a square. Take away 4 quarter circles, which of course is the same as 1 single circle. What about the square? Well, the area of a square is the side itself squared. So for example, if the side of the square was W, then the area would be W squared. So what's the length of the side of my square here? So the square side, I'm going to get them both in the screen at the same time so you can see them. The square side is the x that we're told about, plus one of the radii, plus another radii on the other side. So that's x plus 2a, which means that the area of the square is going to be x plus 2a all squared. And you can square that out, and you might do that in a second, but for the moment we'll just leave it like that. They didn't ask us to write it in a particular format. What about the area of the circle? 4 quarter circles is going to give me 1 full circle, so the area of the circle is going to be pi times its radius squared, but its radius is a, so pi a squared. And that means that the shaded area here is x plus 2a all squared minus pi a squared. You can, if you want to, multiply out those brackets and see if anything simplifies, but to be honest, That's probably the simplest way to write that formula there. If you were to use it, that's neat. If you had to sub things in, that would be a neat formula to sub into. So the area of the shaded area here, x plus 2a all squared, or 2a plus x all squared, minus pi times a squared. Okay, the next shape that we have, another composite shape. And again, every single shape here is either a known shape, take away another known shape, or a known shape added to a known shape. What do we have going on here? We have two semicircles. So this is a rectangle plus two semicircles, which gives us one full circle. So this is one full circle, just like the 4 quarter circles above. My rectangle area is going to be, so you notice I'm doing plus here, where previously I've done minus, because I'm not subtracting the shapes, I'm adding them. So my rectangle is the length times the width, a times b, plus pi times the radius squared. But what's the radius? The radius in this case is half of the diameter, which is a over 2, or a half a. Pi times a over 2. So I might accept this for full marks, but I would like you to at least put the a and the b together like this, and the pi times a over 2 like this. Okay, so I'll give you full marks for that, but we might notice that there's a common term that we can factorize out, giving us b plus pi over 2, b plus a half pi. So that's another way of writing the same thing. Both of those are perfectly valid answers. My preference would be for this second one here, that would be easier to fill into. So the answer here, one possible answer here, is a bracket b plus pi over 2. Now, part E, it's an isosceles triangle, and we want a formula for the area of an isosceles triangle. We know that the area of a triangle is half the base by the perpendicular height. Let me move this over here. Half times the base times the perpendicular height. But we don't know the perpendicular height in this case. But as I've said before, any isosceles triangle can be divided into two equal right-angled triangles. So this right-angled triangle can give us the perpendicular height. This distance here is the base divided by 2, a over 2. This distance here is x, and this is my perpendicular height. So if I want to find the area of this triangle, I need to find my perpendicular height. We can use Pythagoras Theorem, and I know that this is called x here, and maybe we're more used to calling the hypotenuse h rather than this distance here h, but so long as you're careful, what Pythagoras Theorem tells us is that the two smaller sides squared and added together will give us the longest side squared. So that is Pythagoras Theorem. The square on the hypotenuse is equal to the sum of the squares of the other two sides. I can't leave it like that. I now need to manipulate that formula to get h on its own, and then I'm going to substitute that in there. So what we have is that h squared is equal to x squared minus this guy squared, a squared over 4. Remember, when you're squaring out brackets, squaring out fractions, you have to square the top and square the bottom. And we're not done yet, because we don't want h squared, we want h. So h is the square root of x squared minus a squared over 4. And so I use this into my area of the triangle. Remember, the base of the triangle is a. And now I know my perpendicular height. I have a formula for it, that it's the square root of x squared minus a squared over, it's not all over 4, sorry, minus a squared over 4. You could write that as a single fraction, but you don't need to. So that means that the triangle is a half times the base, which is a, times the perpendicular height, which is the square root of x squared minus a squared over 4. That's the difference of two squares, and if you want to do some manipulation with that, you can. So you'll find with these questions, there's almost always several different ways of writing the same thing. But this is a completely valid formula for the area of an isosceles triangle. If you've written it slightly differently because of manipulating your formula differently and you're not sure if your answer is correct or not, you might let me know. Just take a photograph of it and send it to me, and I'll let you know if it's correct or if you've gone wrong somewhere. Okay, finally, an equilateral triangle. So the same exact thing, except in an equilateral triangle, so we can use our previous formula. Can be a bit sneaky here. In an equilateral triangle, it's an isosceles triangle as well, where instead of x, I have a, the same length side here. So if my formula for my isosceles triangle was a over 2, move this over, the formula for the isosceles triangle is a over 2 square root of x squared minus a squared over 4. But we're going to use x is equal to a. And for an equilateral, my equilateral triangle can be a over 2 by the square root of a squared minus a squared over 4. And we can, these are the same terms now, so I can simplify this further. This is 1 minus a quarter, so it's 3/4. So this is a over 2 by the square root of 3a squared over 4. Okay, if you're not following this algebra, you can go back to the beginning and do it by yourselves. Common denominator if you need to. Then, would I leave it like this? Well, remember our laws of surds. So that's a over 2. And the square root applies to every single part of that. The square root of 3, the square root of a squared over the square root of 4. And the reason I did that is because the square and the square root will cancel. And the square root of 4 is just 2. So that's a over 2. I didn't touch it. Square root of a squared is just a. Square root of 3 I can't do anything with. And the square root of 4 is 2. So this finally simplifies down to a squared root 3 all over 4 as my formula for area for an equilateral triangle. So that's a lot simpler than the isosceles one. That's not the only way of finding it. We could have divided this into two equal right angle triangles as well and worked it out from there. So a squared root 3 over 4. And I would expect you to do the simplifying on this, especially at higher level. Okay, so that's getting the formulas for shaded areas. That's a type of question that's quite popular in area and volume questions in Leaving Cert. These two are difficult. So it is something that you definitely want to practice, but it's okay if you don't get it 100% in fourth year. We'll be coming back to it again and again as we do different topics. So area and volume comes up an awful lot with functions. So as we go over other types of questions, you will see these questions again, and you'll get a chance to practice with this algebra again when you're a bit more familiar with it, when you've had a few more years under your belt working with it as well. Okay.